We have already talked of units, dimensions and dimensional analysis. The third key concept of this chapter is measurement and the errors that creep into these measurements. Science is all about measurement, you know that. Precise measurements are necessary to confirm a proposed hypothesis or to choose from among many conflicting ideas the one that is nearer the truth. Importance of accuracy and precision in measurement can be gauged from the fact that at one time, due to lack of accuracy in observational data, geocentric theory was preferred over the heliocentric theory, whereas heliocentric theory was the correct one. The geocentric theory, you remember, held Earth to be the center of the universe, whereas heliocentric theory proposed by Copernicus held the sun to be the center of the universe. It was only the advent of telescope which improved the quality of observations that ultimately vindicated the correct heliocentric theory. So, we may ask a question: what is it that leads to lack of precision or accuracy in measurements? Let us first see the distinction between precision and accuracy. What is precision? Precision refers to the limitation of the measuring device, principally its resolution or least count. Example: to judge the winner of 100-meter race, you have to measure time to the accuracy of 1/100th of a second. So, an ordinary stopwatch with least count 0.1 second is not precise enough. Example 2, a screw gauge with a least count of 0.001 centimeter can measure the diameter of the pendulum bob more precisely than a vernier caliper with least count 0.01 centimeter. Example 3, a telescope with a higher resolving power can measure the diameter of a planet more precisely than a telescope with a lower resolving power. This was about precision. So, what is accuracy? Accuracy tells us how close the measured value is to the actual value. Let us look at examples. 1. You know, a second's pendulum has a time period equal to 2.0 seconds. A measured value of 2.05 seconds for the second's pendulum is more accurate than a measured value of 1.9 seconds. You can see the difference between 2.0, 2.05 and 1.9, and you can see that 2.05 is more accurate. Second example, a measured value of 0.98 volt for a standard 1 volt is more accurate than the measured value 1.03 volt. Once again, you can see why I am saying so. Errors creep into our measurements and affect their accuracy. The errors can be broadly classified into two categories: systematic errors, random errors. What are systematic errors? Systematic errors include errors in the instrumentation, such as permanent shift of 0 of the scale, non-uniform calibration of the scale, poor thermal contact with the substance of which the temperature is to be measured, a stopwatch which is running slow, and a non-uniform resistance wire. All these cause systematic errors. Second category of systematic errors are defective experimental design or techniques, such as holding the thermometer wrongly for reading a temperature, not being able to weigh properly the chemical to make a solution, not being able to figure out the least count of the instrument, lack of skill in drawing a graph, and not being able to remove parallax in optical experiments. Third category of systematic errors are personal errors, such as the tendency of positioning eye to the left or to the right of the point to be read on a scale. Let me remind you, your teacher must have told you that the point that you have to read, your eye must be in line with that point or directly above that point. If you are to the left or to the right of that point, you will not be able to measure temperature correctly. electrical experiments, for example, with the potentiometer, you may not be able to judge the null point properly. That can also cause personal error. What do the systematic errors do? Systematic errors shift the result only to one side. The result is either always higher than the actual value or always lower than the actual result. Random errors, which we shall see presently, can shift the result to either side. So, that is a distinction. Systematic errors are difficult to detect. For example, you do an experiment and you do not know that the calibration of the scale is not correct. Therefore, systematic errors are much harder to estimate than the random errors. They cannot be treated by statistical methods as we do with the random errors. Now, look at a very ideal situation. Even if the instruments are perfect, training in experimental techniques perfect, and personal biases are removed completely, even then the measurements can suffer from errors. These errors cannot be predicted. These are random errors. Let me give you an example. In an experiment using a potentiometer, not all observations of the null point are identical. They show a random distribution. Sometimes they shift to one side, sometimes to the other side. In a simple pendulum experiment, despite extreme care, the observed time periods for a given length show random variations. The time is not always the same. Sometimes it is less, sometimes it is more. Systematic errors in principle can be removed by having better instruments, by perfecting experimental techniques and designs, and by removing personal biases. But random errors cannot be removed. They can only be minimized. Second category of systematic errors are due to defective experimental design or techniques. And what are these techniques? Holding the thermometer wrongly for reading a temperature. If you are not able to read temperature correctly, it will lead to errors. Not being able to weigh properly the chemical to make a solution. Suppose your teacher asks you to make a solution and you are not able to use the weighing device properly, and you are not able to therefore measure the mass correctly. That can lead to systematic errors. Not being able to figure out the least count of the instrument. This error happens very often. I have seen from students from class 12 onwards, even up to MSc stage, students are not able to get correctly many times the least count of the instrument that they are going to use. This is very important, and therefore, if you are not able to do that, your measurements will be in error, and this error would be systematic error. Then lack of skill in drawing a graph. You remember that in many experiments you have to draw a graph. In simple pendulum or in other experiments, you have to draw a graph, and then you are asked to read from the graph time period and length and so on. But if you do not know how to draw a good graph, then again it will lead to errors, and these errors again would be systematic errors. Not being able to remove parallax. When you find focal length of a convex lens or a concave lens or a concave mirror, then you have to remove parallax between the image and the object. You know that if they are not in the same line, then the parallax has not been removed, and this is quite difficult for students. And if you are not able to do that, if you have not learnt the technique of removing parallax, then you will be in trouble. Your measurement would have errors, and these would be systematic errors. Then the third category of systematic errors are personal errors. Many of them I have already enumerated, but let me tell you in detail. Say you are reading a thermometer. In a certain experiment, you are reading a thermometer. Your teacher has told you that the point to be read, note the point to be read, and your eye must be either directly above that point or directly in front of that point. If you are either this way or this way, you will not be able to read the temperature correctly, and this will again lead to errors in measurement. Similarly, in an experiment say with potentiometer, you may not be able to read the null point correctly. When the needle of the galvanometer is not showing any deflection, that is a null point, but you may not be able to judge it properly. This can also lead to errors, and these will be personal errors. Systematic errors, which we have been talking about up to this time, they shift the result only to one side. The result is either always higher than the actual or lower than the actual result. Random errors, which we shall be talking about in a moment, can shift the result to either side. The idea is systematic errors, if suppose you are measuring the melting point of wax, systematic errors will always either measure it lower or higher. Random errors can cause to be measured either lower or higher. Random errors can shift the result to either side. Systematic errors are difficult to detect. For example, doing an experiment, you do not know that the scale is not properly calibrated. How would you know? You do not know that the zero of the scale has shifted. Again, it is very difficult to find out. They are much harder therefore to estimate. Systematic errors are much harder to estimate than the random errors. They cannot be treated by statistical methods. For example, you cannot take averages, as we shall do with the random errors. Now, let us consider a perfect situation. Our instruments are perfect, our training in experimental techniques is perfect, and we do not have personal biases. That means, we do not see this way or that way, say reading a temperature scale. The measurements can still suffer from errors, and these are random errors, and these cannot be predicted. In an experiment using potentiometer, you read the null point, but all the null points are not identical. Sometimes the null point is lower than the previous value, sometimes the null point is higher than the previous value. They show a random distribution. In a simple pendulum experiment, despite extreme care, the observed time periods of a given length of the pendulum show random variations. For example, you are measuring time period for 20 oscillations. The time period at one time may be 30.4 seconds, the next time it may be 29.8 seconds, next time it may be 34.6 seconds, and like that. I mean, you do not know which way the time period is going to be. That is why it is called random. The random error can shift the result to either side. It can be lower than the actual or it can be higher than the actual. Systematic errors, on the other hand, they push the result only to one side. Systematic errors can be removed if we have perfect instruments, if we have perfect experimental techniques, and we remove our personal biases. Random errors, on the other hand, cannot be removed. They can only be minimized. Next time we shall see how we can deal with random errors, so that their effect is minimized on the observations that we take, on the results that we derive, and on the experimental physics.